Hello, hello everyone. So welcome to my presentation, which is on real estate forecasting using machine learning in this project. So what is this project? So this project will analyze, predict, forecast the real estate market analysis and forecasting the using machine learning models. So we'll explore how the simple RNN and LSTM works. We'll discover the trends, analyze, predict, and forecast the trends in real estate market. So I have used real estate data, and the data set is from Massachusetts, which will cover the time period, analyzes effectiveness of this machine learning models, predicting prices and how and predicting the housing prices, and understanding the data set. So this data set contains the information which is related to real estate transaction in Massachusetts, such as sale of date, postcode, property type, number of bedrooms, price. And this data is useful to do the time series analysis and exploratory data analysis, which will help us to look at the trend over the time period. And this data set consists of September 32 7, and the data includes column like data sold, postcode, property type, bedrooms, and prices. So these are used. And by understanding this data, what we can do is we can uncover the temporal dependencies and housing trends, which is useful for accurate forecasting. What are the project goals? So we understand the strength and limitations of simple RNN and LSTM networks, and we apply the pre-processing and future engineering to real estate data. We design, train, evaluate the models for time series forecasting, and we improve network performance by redesigning the LSTM architecture. And we also compare the redesigned model with baseline models. So before that, first thing is say like I keep on saying RNN and LSTM. So what is meant by RNN? So RNN is nothing but a recurrent neural network, which is a type of a neural network designed to handle sequential data like time, series, speech, or text. So it has a feedback loop in architecture, which will allow to be passed from one step to another. So this makes the RNN, which is useful for data matters such as predicting the next word in sentence or else analyzing the stock prices. So where it helps to predict the future stock prices by recurrent neural networks. And similarly, here we're using to forecast the housing prices of the Massachusetts areas price, the zip code, which zip code has a lot of highest price. So why we use an RNN is RNN is used to process one point data at a time and remember the information from previous step using hidden state. So this memory will help us to understand the context and consequences. For example, we use I'm reading a sentence, the cat is on, and then RNN can predict the words like mat, table, because it learns from the previous words, right? Because the cat is on, it make a meaning that where it is on, maybe it may be on mat or it may be on table or it may be on some other stuff. But at least it tries to predict. So this is what is RNN. And what is LSTM? So LSTM is nothing but it's RNN designed to address the problems and vanishing the variance in simple RNN. It introduces the gates which control what information is kept and forgotten or passed to next step. So these can be long-term dependencies better than regular RNNs, but this make them great tasks like speak recognitions, language translations, or time series predictions. Simple example is like if I'm writing a story, I'll mention John. Even if referring to him, the LSTM better who is refer to him 10 sentences later, and LSTS is better determining who John is compared with. I compare John is a thief. If I write 10 sentences compared with that thing, the next sentence it will consider him as a thief. So that means like it learns. It learns from the data and keeps in the memory. So this is what is LSTM. And sine wave predicting. So objectability of RNN periodicity, generated sine wave patterns and prediction closely matched rules. So I have created an RNN. Here you can see I've imported all the packages. I generated the sine wave data. I visualized it. You can see here. And I trained it, and I've added the simple RNN layer, length layer. So, and I did the training, and here it was achieved this training, and here I predicted the predictions and true loss. You can check here. This is a visualizations predictions versus success value, and this is model predictions versus success data, actual data. So you can check here. So what I have achieved. Yeah. So understand the ability of RNN to capture the periodicity and what I tested is the capabilities of simple RNN using the sine wave data to understand the periodic patterns. So the simple RNN is predicted to train this and predict the sine wave amplitudes where it captured the short-term trends effectively and it's trickled with long-term dependencies. So the result is like the predicted sine wave aligned moderately well with true values, which demonstrated the RNN strength in so short-term periodicity, but limitations for long-term context. Insights predictions closely match with the true values. The vanishing gradient problem is hindered. The RNN's performance, which leads to inadequate learning of long-term dependencies. And gradient challenges and LSTM. Yeah, insights. Insights from RSNs through strengths effective for learning short-term dependencies, limitations, struggle with lot of long-term dependencies due to vanishing rights. You can see the predictive sine value variance using RNN. This aims to generate the predictive sine wave using RNN model sine waves, predict the periodic functions. The result is trained on sine wave data which closely align with actual values. So this experimented, I have demonstrated that RNN's ability to learn short-term dependencies. However, the model struggled with long-term dependencies due to vanishing gradient problem. So gradient problem and limitations of simple RNN. So during what is vanishing gradient problem? During backpropagation, gradient decrease complexity exponentially, which makes challenge for the network to learn long-term dependencies. So this problem, particularly in RNNs, as it limits the ability to retain the information over extended sequences. And exploding gradient problem in this scenario, the gradients will grow uncontrollably, which causes the numeric instability and hinders the training process. The exploding gradient problem can result in weight diverging instead of converging, which makes the model unstable and unavailable. The limitations of simple RNN. The simple RNN will face additional limitations, which will include memory capacity, difficulty handling complex patterns, and poor performance on long sequences. These limitations highlight the need for more robust architectures like LSTMs. You can see LSTM addressing the challenges, vanishing the exploding gradient. The key features of LSTM is memory cells retain the long-term information and getting mechanism manage information flows. So time series forecasting. So here I have part four. So here I've imported the packages. I have loaded the data raw sales, which is like the prices, and I have casted. You can see the price, and then after I've used I've shipped the data so 236 to 451 testing it, and I've added the layers LSTM dropout, one dense, and I have run the trained it and I've trained the data. You can see the model over opposite epoch, over epoch. So the purpose is I use the trained data to predict the outcomes of the test data, the model. So the step is crucial to evaluate how well the model organizes the unseen data. And the predictions are stored in the variable predictions. And I have a plot, I'm setting up the plot, setting up the plot, and I have plotted the predictions also. The main reason is predict the values for test. The prediction values holds the model output text data and my stuff. Adding titles, displaying the plot. So overall, I've run LSTM, so which worked and helped to forecast the housing prices in Massachusetts regions. So the LSTM successfully captured the long-term dependencies as reflected in decreasing the violation loss and MAE over. Predictions closely match to the actual data. So in this way, we have achieved uh, the time series forecasting using LSTM. So this part focuses on LSTM ability to capture temporal dependencies and long-term patterns in data. And the LSTM architecture consists of two layers with 50 units, followed by dropout layer, regularization, and a dense layer for the regression output. The LSTM model was trained over 20 epoch and achieved excellent performance. The model validation loss and mean absolute error decreased steadily, indicating the successful learning and generalization. And the data set was real estate data, the model architecture, images, dropout layer, design layer for regression. Effectively captured the temporal dependencies, validation loss, and MAE steadily decreased over epoch. And the redesigning LSTM model. Redesigning is a main motto is to build on the insights from part four where we have kind of signed data. So we redesigned the LSTM model to enhance this forecasting accuracy. So the challenges in architecture, key adjustments which included a third LSTM layer, increasing the neurons to 100 per layer, which reduces the dropout 10%, and which extend the input sequence length to 100 times 10. So the model was trained for 30 epoch with larger sets or display and batch size of 64 for training. And the redesigned model showed lower validation loss and MAE, the predictions aligning more closely to actual values. However, these improvements cost a longer training times and higher computation overload. So overall, the redesigned model, which is demonstrated performance compared to performance to the baseline model, showcasing the effectiveness of implementing implemented modification. Then redesigning the LSTM. So I proposed the changes, added a third layer to LSTM layer, increase the neurons 200 per extended to sequence 2000 per time, increase the POC to 30. So what I have observed is comparison of networks layer. So compare the simple RNN versus LSTM models. So here I show the part 5. You can see I have downloaded the packages and I have generated normal sign data. And I've splitted the data into training and testing sets. I've created the sequences with 60 time step and I reshaped the data for LSTM inputs. And you can check here I have added the LSTM dropout, LSTM on reference layer. So I've added another layer. So you can see the accuracy is more, but if the accuracy is more, the prediction the computation also increased. We generated sine wave and I've trained the data shape and I've added total params, trainable params, non-trainable params, full data to shape. So overall, the computation, the prediction increase, the accuracy increase, but the problem is like uh, the redesigned LSTM achieve lower validation loss and MA compared to the baseline models, which will demonstrate improved accuracy and generalization. However, these improvements came at cost, increased computation complexity, and a longer training data. So the redesign showed that iterative expectations and optimizations can lead to significant performance gain. And what we have achieved comparison of neural network, improved metrics. So the redesigned model achieved lower validation loss and MAE, indicating improvised generation and prediction accuracy. So we have achieved a very good improvised accuracy after adding the layer. Means that if the layer is added, the accuracy will increase, but computation power will be yes. Reason for improvement: the increased number of LSTM layer and neuron will enhance the model's ability to learn the complex pattern data. And this input sequence length enable the model to consider a wider historical context. Limitations: while the redesign led to improved performance, it also increased the computation cost. Training data further increases in model complexity might yield diminishing returns in terms of accuracy level. The lessons I have learned. What lessons I have learned? So with this project, it taught me a lot of key lessons. Pre-processing and data preparations are very critical for the time series analysis, model architecture, and hyperparameters. Tuning the significantly impacting performance, visualizing the result is an essential for evaluating accuracy and identifying the improvement areas. So Simple RNN is a fiction for learning short-term dependencies on periodic table patterns. However, it struggles with long-term dependencies due to vanishing gradients and limited memory capacity. The LSTM overcomes the vanishing and exploiting gradient problems, making it well suited for the modeling long-term dependencies. However, it has high computation overhead compared to the RNN. Here we built, train, and forecast. Pre-processing and data processing are very critical for time series analysis. Model design and hyperparameter tuning significantly impact performance. Visualization of results help evaluate model accuracy and identify areas for improvements. So this project has demonstrated the potential of machine learning for real estate forecasting. So we have forecasted the machine learning. Yeah, we can check this is the data. So yeah, so we have used. Yeah. So this project demonstrated use of machine learning models for real estate time series forecasting. Through this analysis, we learned that simple RNN and LSTM networks. We learned the strength and limitations, how the LSTM effectively addresses the vanishing gradient problem, which leads to more accurate predictions. The redesigned LSTM models outperform the original, showcasing the benefits of iterative experimentations and model optimizations. While the project faces computation cost challenges, the dataset limitations, but it has served valuable starting points for exploring various model work architecture. So you can see the redesigned results, lower validation loss, and EMA forecast closely aligned with actual data. Challenges is being user computation and training time. So we have added the third layer to LSTM, which increased the neurons to 100 per extended the sequence length 100 time step, and we increased the epoch. And we compared the performance. We have redesigned the model, which achieved the better generalization and long-term sequence length, improved the context understanding. And what lessons we have learned? The simple RNN, we effectively use the RNN for short-term dependencies and where it struggled with long-term dependencies. The LSTM addresses the gradient issues and which is also suitable for long-term dependency modeling. And the conclusion, we have LSTM networks perform simple RNN in forecasting accuracy, and we have redesigned LSTM further improve the performance. The future work explored GRU transform models with richer datasets. So overall, this project demonstrated the potential of machine learning use in real estate forecasting. And this networks performed simple RNNs for vanishing gradient issues. The redesigned LSTM model showcased the importance of iterative optimizations. The future work could explore more futures, large data sets, and iterative architectures like transform models to further enhance the forecasting accuracy. So you can check in part two. I have generated the sign data, and in part four, I have used the data set here, original time series data, and that changed the data. You can see the model also over epoch and model over epoch, MA over epoch. So I've trained and model 5 can check. I've added another layer. These are redesigned. So, and I've forecasted this, and the model was pretty good. But accuracy and the prediction was fine, but only the accuracy level, the computation power is overheaded. So that's the reason. So coming to, yeah. So the data set where I took the data set one, I took the data set from Cackle. So the real estate data, as I already told you in the first thing, I have selected this data, real estate sales data, and this data contains information which is related to real estate transactions, such as dates of sold, postcode, price, type of property, and number of bedrooms. The location selected is Massachusetts, and this data set will try to improve some insights in housing trends for that period. So we have data sold, postcode, property type, bedroom, and price, as I told you, and this data has numeric and string values, and I took this from the Kaggle. So these are my observations. So with this data, what we can do is we can do this data market trend analysis. We can do a property valuation studies. We can do the real estate investment insights, policy, urban planning. What we can do with this data is a challenge because we can do a lot of things. Um, Really, like for example, if I want to invest in the Massachusetts in future, like now, I can just check the future predictions. If I invest 10 or 100K dollars here, maybe I can expect predict this the price after 2 to 3 years so that it can increase. So depending upon the predictions, I can um, purchase or invest on property. So this data had a lot of issues. So we need to data conversions. We need to have a data handling missing issues, categorical data encoding, normalization, explorated data analysis. What are the challenges as I have faced is I have lack of metadata and geographical specificity. They only gave the zip code, so it's very difficult for me to analyze. Limited availability. There are only 4 columns, and which pertains to Massachusetts. It's lack finer geographic segmentations. Limited variability. There are 4 only columns in the data set, which narrows the scope of analysis if the data set included more attributes such as square footage and year built and property conditions. Then the analysis will be in more depth. Recommended improvements. So we will enrich the data set by adding more features to the data set like property location, information, any other information that can help us in deepening our analysis, where we can find a lot of insights. Because here in the data, we only see the property type, bedrooms, and uh, the price, bedroom, and the year. So other variables, so if added, we can deepen our analysis when we can derive more in the insights. Recommended improvement and data quality assurance. So we'll verify the consistency of records, especially in the sale data, which will ensure the accuracy of results. And overall, we have used the real estate data, and I have used in the first part. I've explained the data set in the document. I've understand the data set, and I've conducted the LSTM model on this thing, and I've forecasted, trained the data, and in the part five, I've redesigned it with adding a new layer, so it worked. The accuracy was increased, the prediction increased. The problem is computation overhead will increase or will increase, so that affects. And when I compare with adding the both layers, so both layers, so lower validation loss and MAE is drawn, and are forecasted closely aligned with the actual data. Challenges to increase competition. So these are the challenges, and overall, I worked on all these aspects and forecasted the real estate price, and even answer the solving gradient problems and vanishing gradient problems. So what I've concluded is the LSTM network outperforms Simple RNN in forecasting accuracy. The redesigned LSTM further improved the performance, and further future work we can explore more GRU and transform models for the richer data sets. So thank you so much.